Okay, in this question we're going to see a recurring theme start to develop, which follows on in the rest of the questions. So I'll be referring back to this one fairly frequently in similar questions in the rest of the worksheet. Here we're asked to calculate the shaded area. Now, the very first thing to do is to draw just one of these sectors by itself. So I'm going to take this shape over here and draw that by itself. Now, I can work out this shaded area in here by doing the area of the whole sector and taking away the area of this triangle formed by cutting straight across that line there. Now, the area of a sector formula is the fraction of the circle we're dealing with, theta over 360, times the area of the circle itself, pi r squared. And the area of this triangle is a half AB sine C. But of course in this case A and B are both the radius, so I can replace A times B with r squared, and C is the angle in the centre, which I've just labelled as theta. You don't need to memorise this as if it's a new formula, I'm just relabeling it for the purposes of the circle. So the area of this shaded bit in here is the area of the whole sector minus the area of that triangle. Now in terms of the original problem, that would be this area that I've shaded in over here. And essentially once I've worked that out, I can double my answer because it'll be exactly the same on the other side. So I've got 40 over 360 times pi times 10 squared minus a half times 10 squared times sine 40. And that's the area of one of those shaded bits. I'm going to call this A, so it's got a name. And that's all going to go into my calculator all at once. So 40 over 360 times pi times 10 squared minus a half times 10 squared times sine 40. That's all coming out as 2.767. So the shaded area is just double that. And that's coming out to be 5.53 centimeters squared. So this principle of getting this area over here by doing the sector area minus the triangle area seems to be asked about quite frequently on these papers. This particular question is slightly more devious in that they're actually overlapping. So ironically the hardest one has appeared first on the worksheet. Apologies about that. Let's move on to the next question, but remember I'm going to refer back to this principle next time we see this problem. So here we have a little bit of a holiday. We're asked to calculate AC, which I will label as x. I need a formula that's going to help me with this. And in this problem I have two sides involved and two angles involved. So I want a formula using two sides and two angles, and well, that's going to be the sine rule. Using this opposites principle, so I can substitute in correctly, that is x over sine 30 is equal to 8.15, using the opposites again, over sine 110. Multiplying both sides by sine 30 and working everything out will get me the value of x. So I'm going to go straight ahead and do that now. So sine 30 times 8.15 divided by sine 110 altogether has given me x equals 4.34 centimeters for that side. Now this next question is an example of where we're going to have to look for two possible values of an angle. This is the principle that there can be acute and obtuse solutions for a sine question. So let's go through and see what we've got. In a triangle PQR, PQ is 8 and QR is 7, and the area of the triangle is 17 centimeters squared. So, we want to find possible values of the angle PQR. So, let's label this point Q over here. I know that PQ is 8, so I'm going to draw that going off over here maybe. Let me just draw a straight line. So I'm going to label P over here, and PQ is 8 centimeters. Now QR is 7 centimeters. Now I could draw R over here, and that will be 7 centimeters. But I could also draw R over here, and call that 7 centimeters. So I could have the triangle PQR drawn like this, or the triangle PQR drawn like this. Either of these two triangles could have an area of 17 centimeters squared, meaning I'm either going to get an angle over here, or I'm going to get 180 minus that angle over here. Now you might look at these two triangles and think, well, they couldn't possibly have the same area, but if we go back a few stages in our understanding of triangles and think about a half base times height, both of these triangles have the same base, and they both of them reach the same height, the height where P lives. So they would both have a half times the same base, 7 centimeters, times the same height. So both triangles are valid. Now you don't have to be able to construct both of these triangles to answer the question. If you remember that whenever we're after two possible values of an angle, in a question involving sine, we get one of them from the calculator, and the other one by doing 180 minus that angle. If you just learn that fact, you don't need to worry about everything I've just said. So, let's now work out how to do the problem. I'm going to focus on this triangle over here. I know something about area, I know something about length, and I want to know something about an angle. So the formula that puts all this together is area equals a half AB sine C. Here's my A for area sitting in here. So I know that the 7 and the 8 and that angle all go together in that area formula. Substituting in, 17 equals a half times 8 times 7 times sine theta. So 17 is equal to 28 sine theta, and I can get sine theta equals 17 over 28, take the inverse sine of 17 over 28 and get an answer. The inverse sine of 17 over 28, that's equal to 37.4 degrees. That will be the angle in this triangle. If I was looking at the other triangle, I would need the other side of this line, 180 minus 37.4. And that would give me 142.6 degrees, or to three significant figures, 143 degrees. Again, if I'm not happy working out the triangles, I can simply remember to do this 180 minus thing whenever asked for two possible values of an angle in a question involving sine. So we've just looked at two quite complicated questions with an easy one in the middle. I'll do more solutions in the next video.